Gases, mixtures, and movements. We'll look at two more gas laws here. Dalton's law deals with partial pressure. Gas pressure depends on the number of particles in a given volume and on the average kinetic energy. Now, particles in a mixture of gases at the same temperature have the same average kinetic energy, so the type of particle is not important. We could look at any number of gases. The type of particle is not important. The contribution each gas makes to the total pressure is called the partial pressure. In a mixture of gases, the total pressure is the sum of the partial pressures. So P total equals the sum of P1 plus P2 plus P3 and so forth. Dalton's law says the total pressure exerted by a mixture is equal to the sum of the partial pressures. So if I have a mixture of gases, for example, air is composed of oxygen, nitrogen, argon, water, and carbon dioxide. All I have to do is simply add up the partial pressures. So the pressure of oxygen is 20.9, nitrogen is 78.1, and so forth. If I add up these five gases, I will get the pressure in air at 101.3. So the first example, determine the total pressure of a gas mixture contains oxygen, nitrogen, and helium. I want to find the total pressure. So P total is simply equal to the sum of the partial pressures, which in this case we got 20 plus 46.7 plus helium is 26.7. So that's all we have to do to get the total pressure in kilopascals. Very straightforward gas law. 93.4 kilopascals. A gas mixture containing oxygen, nitrogen, and carbon dioxide has a total pressure of 32.9. If I know oxygen and nitrogen's partial pressure, what is the partial pressure of CO2? Well, I would simply take the total pressure and subtract the partial pressures of oxygen and nitrogen. So the partial pressure of CO2 is 3.3 kPa. So that's all Dalton's law is. The last gas law is Graham's law. Molecules of a gas diffuse or spread out through space. So molecules will spread out to areas of lower concentration. The other process that involves movement of gas is called effusion. During effusion, a gas escapes through a tiny hole in a container. So like when the helium escapes through a tiny hole in the balloon, that's why your balloon deflates and sinks, because the helium is effusing out of the balloon. The type of gas particle is important with diffusion and effusion because gases of lower molar mass diffuse and effuse faster. So Graham's law relates the rate of diffusion or effusion with the molar mass. And here's what Graham's law looks like in a mathematical expression. Rate of gas A over rate of gas B is equal to the square root of the molar mass, gas B, over molar mass of gas A. So in a mathematical expression, that's what Graham's law looks like, and the type of gas is important. So in this first example with Graham's law, what's the rate of effusion of helium to nitrogen? Helium is going to be gas A because it's listed first in the problem. Nitrogen is gas B because it's listed second. So then we have the square roots, molar mass of N2 on top because it's inversely proportional, molar mass of helium on bottom. We're going to plug in the numbers that we know for molar mass. N2 has a molar mass of 28. Helium has a molar mass of 4. So 28 divided by 4, take the square root. We get 2.65. And we have to make a comparison here. So what is the rate of effusion of helium to nitrogen? It's always compared to 1. So 2.65 to 1. And what this means is helium effuses 2.6 times as fast as nitrogen. And that makes sense because helium has a lower molar mass compared to nitrogen, so it should effuse faster, and it effuses 2.6 times faster than nitrogen. Let's look at one more problem. Calculate the ratio of the velocity of helium to the velocity of fluorine. Well, we're still looking for rates, and since helium is listed first, it's going to be gas A. It's going to go up here on top, and then fluorine molecules. Fluorine is diatomic, so that's F2. Molar mass of F2 would go on top. Molar mass of helium would go on bottom. Plug in our numbers. Fluorine, F2, has a molar mass of 38. Helium is 4. Solve this. 38 divided by 4, take the square root. You get 3.08. And again, we have to make a comparison because it says calculate the ratio. Well, the ratio is 3.08 to 1. So helium atoms are 3.08 times faster than fluorine molecules.